Your agent worked great in development, maybe a few dollars a day, then you pushed it to production and suddenly you're looking at $500 daily API bill. The problem is twofold. Your users keep asking similar questions and every single one triggers a fresh API call at full token cost. On top of that, there's nothing stopping a single complex request from burning through your entire budget in one shot. Today we are fixing both of these problems. We're building a semantic cache with Redis that catches repeated and similar queries and a token budget system that puts hard limits on spending, all in Python with LangChain and tick token. Let's get into it. To understand why agents are so expensive, you need to look at the call pattern. A single user request doesn't mean a single LLM call. Your agent might call the model 3, 4, even 10 times as it reasons through tool use and follow-up steps. Each of those calls includes the full conversation context, tool schemas, and the model's reasoning, so token counts add up fast. Now multiply that by hundreds of users asking overlapping questions and you start to see why that bill climbs so quickly. The key insight is that many of these calls are either identical or semantically equivalent to queries you have already processed. We are going to implement two complementary systems. The first is semantic cache powered by Redis, which intercepts query before they hit the API and checks whether we have already answered something similar enough. Unlike exact match caching, semantic caching uses embeddings to catch paraphrased or reworded versions of the same question. The second system is a token budget manager that enforces hard limits on how many tokens any single request or user can consume. Together, these two layers give you predictable calls without degrading the quality of your agent's responses. Here is the flow for the semantic caching. When a query comes in, we first convert it to an embedding vector using a lightweight embedding model. Then we search Redis for any cached query whose embedding is within a configurable similarity threshold, typically around 0.85 to 0.95 cuisine similarity. If we find a match above that threshold, we return the cached response immediately without ever touching the LLM API. If there's no match, we forward the query to the LLM as normal and then store both the query embedding and the response in Redis for future lookups. The important thing to notice is that the embedding call is extremely cheap compared to a full LLM completion, so even cache misses at negligible overhead. Token budgets work as layered guardrails. At the lowest level, you set a per request limit that prevents any single query from consuming an unreasonable number of tokens. This catches things like runaway, agent loops, or unexpectedly large context windows. Above that, you track per user daily consumption, which lets you throttle heavy users or implement tier taxes. And at the top, you have a global daily budget that acts as your absolute safety net, ensuring your total spend never exceeds what you have allocated. We use tick token to count tokens before and after each call, so you always know exactly where you stand relative to each budget layer. Now that you understand the architecture, let's implement it. We will start by setting up our project and Redis, then build the semantic cache layer, add the token budget manager, and wire everything together. The full implementation is around 100 lines of code, and by the end you'll have a drop-in system you can add to any LangChain based agent. Let's now start by creating a new folder and moving inside of it. Next, we create the new Python virtual environment and we also activate it. Now let's install our dependencies and make sure Redis is running. We need LangChain OpenAI for the LLM integration, LangChain Redis, which is the official LangChain partner package for Redis caching and vector search, and tick token for accurate token counting. We are using LangChain Redis here instead of the older LangChain community Redis cache because the community version has a non-compatibility issue with the latest Redis Python package. The partner package is actively maintained and works out of the box. If you don't have Redis installed locally, the easiest way is to spin it up with Docker Desktop using the Redis stack image, which includes the vector search module we need for semantic caching. Inside the .env file, we also need to specify our OpenAI API key. And next, we create a new file called AgentCostOptimizer.py. Here we start with our imports and configuration. We are pulling in tick token for token counting, LangChain OpenAI for the LLM and embeddings, and the Redis semantic cache from the LangChain Redis partner package. We also import setLLM cache from LangChain core globals, which lets us register our cache globally so every LLM call uses it automatically. We load the API key from an environment variable, which you should always do rather than hard coding secrets. We also initialize the tick token encoder for the specific model we are using. This matters because different models use different tokenizers and you want your token counts to be accurate. Next, we built a simple utility function for counting tokens. This function takes any string and returns the exact number of tokens it would consume for our target model. We use tick tokens in code method, which returns a list of token IDs and then just take the length. This might seem trivial, but having an accurate count before you send a request is the foundation of the entire budget system. Without this, you're guessing at costs, and guessing is what got us into trouble in the first place. We also add a cost estimation helper that multiplies token count by the per token price so we can work actual dollar amounts later. Now we build the budget manager, which is the core of our cost control system. This class tracks token usage across two dimensions, per request and per user daily totals. When you call check budget, it first looks at whether the estimated tokens for this request exceed the per request limit. If that passes, it checks the user's accumulated daily usage against their daily cap. The important design choice here is the estimated output parameter. We check budgets before making the API call, not after, so we need to estimate how many tokens the response will use. You want to tune this default based on your typical response lengths. We are storing usage in a simple dictionary keyed by user ID and date. In production, you would want this in Redis or a database for persistence across restarts, but for our purposes, this keeps the logic clear. We need a method to record actual token usage after each call completes. The spend method takes the user ID and the real token count from the API response, then adds it to the daily total. We also return a summary dictionary with the running totals and estimated costs so far, which is useful for logging and for showing users how much of their budget they have consumed. This is where the estimate cost function from earlier comes in handy. Here is where we set up the semantic cache using the LangChain Redis partner package. The Redis semantic cache takes an embeddings model, the Redis URL, and a distance threshold that controls how similar a new query needs to be to a cached one in order to count as a hit. This parameter uses cousin distance, where 0 means the vectors are identical and higher values are less similar. A threshold of 0.2 is a solid default. It catches obvious paraphrases without returning irrelevant results. If you want stricter matching, lower it to 0.1. We also set a time to live of 1 hour so cached entries expire automatically, which is important if your underlying data changes. After creating the cache, we register it globally with LangChain using setLLM cache. From this point on, every LLM call made through LangChain will automatically check the cache first. You don't need to modify your existing agent code. Now we tie both systems together in a single query function. This is the function your agent or application will call instead of invoking the LLM directly. First, we count the input tokens and check the budget. If the budget check fails, we return an error immediately and no API call is made, and so there is no cost. If the budget is fine, we call the LLM through LangChain, which automatically checks the semantic cache before hitting the API. After we get a response, we determine whether we got a cache hit by measuring the response time. Now, the threshold here matters. We use 1 second, not 100 milliseconds, because even cache hits require an embedding API call to compare the query against cached entries, and that call alone takes 200 to 500 milliseconds. The actual LLM completion on a cache miss takes 2 to 10 seconds, so 1 second gives us a clean separation. Here is the other key detail. We only record spending when it's a cache miss, because cache hits don't consume LLM tokens. This means your budget only tracks real spent and cached responses are essentially free. Now let's test this end to end. We'll send 3 queries. The first is a fresh question that will miss the cache and hit the API. The second is the exact same question, which should be a cache hit. And the third is a paraphrased version of the same question, to test whether semantic similarity catches it. We print the result for each query, including the latency, so you can clearly see the timing difference between cache hits and misses. When you run this, the first query should take a few seconds since it's a full LLM call. The second and the third queries should return under a second because they only need the embedding call to match against the cache. Notice that the daily usage counter only increases on the first query. The cache hits don't consume any budget. Now let's see this in action. In our terminal we type python agent-cost-optimizer.py and we run it. And when it's done executing, you can see that the first question didn't hit the cache and it took almost 17 seconds, where the second and the third one took less than a second and they hit the cache. The second and the third one also didn't consume any usage. And finally, let's verify the budget enforcement actually works. We will create a second budget manager with a very low daily limit of just just 1000 tokens and simulate a sequence of requests, each consuming 400 tokens. After 2 requests, we will have used 800 tokens, and the third request estimated total will push us past the 1000 token limit, triggering a block. This is exactly the behavior you want in production. When a user or a runaway process hits their limit, the system fails gracefully with a clear error instead of silently racking up charges. In real deployment, you would return this error to your API layer and respond with an appropriate HTTP status. And now, let's test the budget as well. As you can see at the bottom, the first 2 requests were allowed and the second and the next 3 requests were blocked because the daily limit was exceeded. Let's recap what we built. We started with the problem, agents making redundant API calls with no spending guardrails. We then implemented a semantic cache using Redis and LangChain that catches not just identical queries but semantically similar ones, skipping the LLM entirely for cache hits. On top of that, we added a token budget manager that enforces per request and per user daily limits, blocking requests before they cost you money. Together, these 2 systems can realistically cut your API costs by 60 to 80% depending on your query patterns. From here, I would recommend tuning the similarity threshold for your specific use case. Start at 0.90 and adjust based on whether you're seeing false positives or misses. You should also set a time to live on your Redis cache keys so stale responses expire automatically, especially if your underlying data changes frequently. If this saved you some money, subscribe to ByteBuilder for more production-focused AI engineering content. I'll see you in the next one.